Hi everyone, we are the group 6 and the purpose of this video is to introduce, summarize and present our project that is a design and simulation of a centrifugal pump. The content of the video is divided in multiple sections. We are going to start with the goals, then introduction, context, results and analysis, comparisons, and finally the conclusions.
For the purposes of this project, we look forward to run 5 simulations and a few others, seeking to study the behavior of a centrifugal pump, of which 3 meshes were made to establish which one was the most optimal. This is briefly summarized in the design and simulation of the pump, recognizing the physical models that govern it, using Inventor 2021 and Star CCM plus softwares.
First of all, it's important to understand the definition of a pump, and pumps are turbomachines that change kinetic momentum of a fluid to make the transport of this one easier and automatic. The main parts of this equipment are volute, impeller, and blades. The behavior of these pumps can be predicted through a simulation in 3 steps. The first one is the creation of a geometry model of the pump. Then we need to put the reference values and fluid characteristics. And the last step is the simulation using star CCM+.
First of all, it's important to mention that equation of states such as Navier-Stokes describes the conservation of momentum, which has made it possible to build airplanes, cars, and turbomachines. This is because they describe the behavior of fluids according to their properties and conditions like density, viscosity, temperature, and pressure. Furthermore, CFD consists in applying methods such as the Reynolds average Navier-Stokes that allows modeling turbulence in a suitable way on steady-state fluids, with the respective assumptions such as K epsilon turbulence, constant density, three-dimensional flow, among others. Its history goes back to the linearization of the Euler's equations, which allowed the development of two-dimensional methods in the early 20th century, to be later improved covering a wide range of restrictions. Thus, John Hess and Amy O. Smith are credited with the first three-dimensional algorithm in numerical analysis for fluids problems. Later, Brian Spalding and Suhas Patankar, who can be seen in the photo, incorporated it as a computational method at the end of the century, representing minimum expenses and security when purchasing and installing operation in turbo machines. Also, companies such as NASA or Boeing developed codes adjusted to their needs for the modeling of fluids such as air, which allowed important scientific advances. In this way, it was very useful to carry out our objectives and could be useful for people interested in the study of fluids in the centrifugal pumps.
The most important parameters of design are showing right now on the screen. And the meshing, we use a polyhedric mesh, and the transition of the growth of the cells was with 3 meshes: the fine, the normal, and the thick in the base size. The flow was simulated with a turbulence model. That means that was necessary to use a K-epsilon model, and the reason is because this model allows to run simulations with a high Reynolds number. Other of the advantages is that this method has a good convergence and low memory requirements. In terms of suppositions and boundary conditions, we assume a steady state, a constant density, and the values of the viscosity and gravity. Also, in the inlet region, we put the value of the mass flow rate. This is the geometry for the impeller. You can see the inclination of the blades backwards, and the tips of the blades are rounded. Also, you can see all the dimensions and the principal angles that contains the impeller. In the volute geometry, we can say that the cut water is smooth. Also, the volute profile is circular and fits the impeller discharge. This is the assembly of the volute and the impeller.
In order to select the most efficient mesh, it's necessary to generate three different meshes: a theme one, a reference one, and a thick mesh. It is important to mention that the mass flow rate used for the simulation was the one given by the manufacturer. The first mesh created is the one called reference mesh, with a base size of 0.02 meters. One of the requirements of this mesh is that the number of cells must be around 1 million plus or less 10%. Now for the results, we have an efficiency of 66.9%, a total head of 150 meters, a CPU time of 24,639.9 seconds, and a brake power of 85,200 watts. The thin mesh, with the 30% less of the reference base size, displays an efficiency of 66.6%, a total head of 114 meters, CPU time of for the 17,302.02 seconds, and a brake power of 85,200 watts. Now, finally, the thick mesh, with the 30% more of the reference base size, displays an efficiency of 67.8%, a total head of 114 meters, and a CPU time of 5,136.58 seconds, and a rate power of 85,330 watts. Analyzing the results previously described, it is clear to see that the better mesh for the design of the pump is the thick mesh. This due to its high efficiency and the low CPU time taken to generate the mesh. Now, after selecting this mesh, which parameters are defined by a target surface size of 100% relative to base, a minimum surface size of 13.5 relative to base, a number of thin layers of 3, and a number of prism layers of 4, a prism layer stretching of 1.2, and a prism layer total thickness of 0.00234 meters. It is necessary to run the reports again in order to determine the worldwide plus, obtaining 124th as a result. It is important to mention that this is an unexpected result because normally the worldwide plus must be minor to 5. Nevertheless, this might be due to errors in establishing these parameters, and it indicates that the mesh is not refined enough, implying that it is difficult to have a good approximation to the viscosity sublayer near the wall. Once the mesh and the reports are generated, 5 simulations for water and 5 simulations for mineral oil were run. For the water reports, the 5 simulations were done at the following mass flow rates: 0, 19, 182, 210, and the BEP, which in this case is 224 cubic meters per hour, obtaining that the pump design is better than the one given by the manufacturer. This is because the efficiency is higher in this pump and it requires less CPU time to compile 1000 iterations. Also, the brake power is higher, same as the worldwide plus. However, this last one means that the mesh must be improved. Now for the oil report, the 5 simulations were done at the same flow rates except from the BEP, which in this case is 214, obtaining from a minimum increase and efficiency that the design pump is better. Nevertheless, it took more CPU time to run the simulations with this substance, and it also have a bigger worldwide plus. In terms of the worldwide plus for the mineral oil, both design and manufacturer pump have great values, which means a great proximity to the viscosity sublayer. This because they are less than 5.
Next, we have some scenes that show the behavior of different factors through all the pump. First, we have the absolute total pressure that goes from minus 1.43 megapascals to 2.4 megapascals. And in the case of the oil, we see that it doesn't vary very much from simulation to simulation, but in the case of the water, we can see that first, in the middle of the pump, the pressure is lower, and it also goes down when the flow increases. Next, we have the vectorial velocity that goes from 0 to 62 meters per second. And here we can see that the behavior is even between oil and water, but they both have the characteristic that in the impeller, we can see that the velocity is higher and it goes down as it flows through the volute. For the Y plus, in the case of the oil, we had pretty low values, which means that near the wall, the simulation adjusted pretty well. We had a pretty different scenario in the case of the water because the Y plus values were near 122, pretty high, and this may be because the viscosity of the water is less, so they can develop a more turbulent flow, and it's harder for the mesh to simulate the behavior near the wall. For the cavitation, we established the steam pressure for the oil in 0.0052 pascals, and we here show the spots that have a higher pressure than this. We can see that we have very few spots, and these are mainly concentrated in the impeller.
Now we are going to talk about the pump operation curves. Analyzing the head versus flow graph, it can be seen that the water and oil curves are below the manufacturer's curve until the 200 cubic meters per hour. After that value, we can see that the curve of the water uh, reaches the curve of manufacture. Analyzing the efficiency versus flow rate graph, it can be seen that the water and oil curves are below the manufacturer's curve until the value of 200, 210 cubic meters per hour. After that value, the curve of the water reaches the manufacturer's curve. Analyzing the brake power versus flow rate graph, it can be seen that the three curves have a similar growth behavior.